Start. Hello, everyone. Thank you all for coming, and welcome to this 7th session of our online seminar on optimization. Today, I have the pleasure to introduce my dear friend, Sebastián Tapia-García. Sebastián is going to give us an introduction and a discussion on weak KAM theory. So, please, Sebastián.
Okay, thank you for the introduction. And yes, so today I will do a talk about a theory that actually I just get to know 2 years ago, more or less. And I realized that some of the work that I have done can be also seen from the perspective of this theory. And so for that, I want to explain more or less which are the gist or the main concept of what is called weak KAM theory. And then, if time allows, I will explain how this relates to my late work. Okay, so first, weak KAM theory was mainly developed by Albert Fatih at the end of the 90s, beginning of the 20s, or the basis of the theory. And then for sure it has been a growing subject of study. But let's start with something that more or less we all may know. So let's omega be a bounded open set on Rd, L a continuous function, bounded, positive, and G a function on the boundary. So the equal equation reads as follows. And it is known that up to a compatibility condition between the data L and G, we can find a continuous viscosity solution given by the following formula, which is actually somehow for each x is the cost of moving from x to the boundary through the function L. And we have the following inequality estimate that if we take x and y in omega, then the value of Vx minus Vy is controlled by the integral of L along any curve connecting x and y through omega. Okay, this is just due to dynamical programming. So somehow this page has more or less 2 out of 3 of the main ideas of the theory that we will discuss in some minutes. So the setting. M will be a smooth connected compact Riemannian manifold.
So, we had some bandwidth issues. So you froze just after saying the first hypothesis.
So you choose your favorite. H. The what?
You froze. So you froze.
Okay. And I'm still frozen? Okay. And H is a C2 Tonelli Hamiltonian. That means it's a function defined on the cotangent bundle of our manifold, such that it's super linear, uniformly on X, on the momentum variable or in the P variable, and also is uniformly convex. The classical example of such a Hamiltonian is just hx equals to 1/2 of p squared plus v, where we can imagine that p is sort of a momentum and v is the potential energy of a system, if we want some physics interpretation. Okay, we are interested in the following equation. So h evaluated at x dux equal to a constant for all x in our manifold. So first, the first difference with before the equal equation is that we don't have boundary necessarily. Yes, so we need to do something with this. And we need to define 2 different things. First, which is the right constant for this equation to make sense? And second, which is the notion of solutions, if we would use viscosity or another kind of solutions. Okay, so let's go first for defining the constant. So CH is called nowadays the Magne critical value, and it is as follows: is take any C1 function on the manifold, compute the maximum of the values of the Hamiltonian, and take now an infimum on this family of functions. So, okay, this is a number that can be estimated. Actually, if we choose u a constant function, we will have that at the right-hand side, we have a maximum of h of x comma 0. So we have the first inequality. And if we realize that any C1 map on a compact manifold has a critical point, then we will realize that for any function u, this maximum is greater than the minimum of hx0 with x in m. And moreover, in the very simple case of the mechanical Lagrangian, we can compute the Mañé constant as the maximum of what we have called the potential energy. Okay. Moreover, to give a bit more importance to this constant, if u is a C1 function, then always the minimum of the values of the Hamiltonian evaluated in x dux is lower than this constant. How to show this? Well, take any function C1 smooth, and we realize that the difference, u minus v, has a critical point on the manifold because the manifold is compact. Therefore, there is one point in which both functions have the same derivative. Now we take minimum on the left side, maximum on the right side, infimum on v, and we have this conclusion. What says this? Actually, if u is a C1 smooth solution of our equation Hamiltonian equal to a constant, then the constant should be the Mañé critical value. So this is the first, first thing that we can see, that the Mañé critical value may be the right constant for but you may also think that one smooth solutions, which is true. And moreover, the constant CH is meant to destroy somehow the C1 functions or the C1 solutions, because infimum of C1 functions are not necessarily C1. Okay.
It frozen here. Yeah, Seba froze again. So let's wait for him to come back.
So now we go with the a posteriori, define what is a solution. They will tell me when I'm not frozen.
Yeah, you were frozen just at the end of the previous slide.
Okay, so
you mentioned that the infimum of C1 functions is not C1, and then you froze.
Okay, yeah, good. So now we want to define the right notion of solution, and this will take us some time. So for a Lipschitz function, we will say that u is a critical subsolution, and we denote it by u belongs to SSH, if hx du is lower than ch, our Mañé constant. Here we can recall that Lipschitz functions are differentiable almost everywhere, thanks to Rademacher theorem. No? So the first property that we have of the subsolution is that it's a set which is non-empty. Okay. How to prove it? We go before, we take an infimizing sequence of C1 functions, and we use Archer-Ascoli because they will be equilipschitz due to the coercivity of the Hamiltonian H. Okay. Moreover, again, the convexity of the set of subsolutions comes from the fact that H is convex and the closedness as well. Also, the set of subsolutions quotient with the constant, because our equation does not depend on the values of u somehow. So if u is a subsolution, u plus 3 is also a subsolution. Is the set of subsolution is compact when we quotient this with the set of constant functions for the uniform topology. And how to prove this is because we have that H is superlinear. So if we have that this is bounded, then all the derivatives of our subsolutions are bounded. Since they are Lipschitz, well, they are equi-Lipschitz. Okay, this definition is somehow could be more or less cryptic, but to work a bit further, we need an alternative definition that can be done with the Lagrangians. So we recall that the Lagrangian associated to our Hamiltonian is just the Fengel conjugate of the Hamiltonian in the cotangent bundle. So since the Hamiltonian is Tonelli and C2, we can also prove that the Lagrangian is also C2 and Tonelli. So that means also that we can use all the machinery of Euler-Lagrange theory. Okay, so the first proposition, how to characterize critical subsolutions. Actually, U is a subsolution if and only if we have the following inequality. The difference in value of U on gamma B and gamma A is controlled by the cost that we obtain by integrating the Lagrangian plus these critical constants times the time that it takes for the curve. And this holds for every curve gamma. The first thing here is that we recall that U is a critical subsolution if it's Lipschitz and satisfies the inequality with the Hamiltonian. So this inequality provides us Lipschitzianity by itself, and moreover, well, the inequality. So we can take infimum over all the curves. We take outside the constant time b minus a, and we define this function h b minus a y x, which is basically the minimal cost that we have for going from y to b in time b minus a. For sure, since our Hamiltonians and Lagrangians are as smooth as we want and as convex as we want, this infimum is in fact a minimum, and the solution satisfies the Euler-Lagrange equation. Yeah, and okay, so just which is behind this proposition is only the Young-Fengel inequality. Okay, so now we have to do a choice. What is more important for us? Like that the curve starts in A and goes to B, or that the curve ends in B but comes from A. Somehow, since we are optimizers, let's say, and we think always that we want to go to the minimum, we will do we will take the option that the important part is the curves ends in B and comes from A somehow. So it comes from a place in which it should be a critical value. With this, we define the Lax-Oleinik semigroup, which is we take a function u and we evaluate it at the semigroup at time t, which is I take the infimum of all the curves that start in minus t and arrive at time 0 at x. So in
Frozen, the difficult.
With frozen, I guess.
It's frozen.
with our definition of the function or the minimal cost that it takes from going from.
So you froze again when you were giving the definition of the semigroup.
Okay. This is frozen too often. I'm very sorry for that. Okay, so the semigroup is we take our point x and we move with a curve from time minus t to 0 and okay, we take this infimum. So here, as we said before, the important part is that the curves arrive at x in time 0, and z is free behind. For sure, again, since n is compact, this infimum is attained. TT can be shown that it's a continuous non-expansive semigroup with respect to the infinity norm, and the set of subsolutions is invariant with respect to the semigroup. And now we recall that the semigroup, the subsolutions quotiented with the constant are a compact set. So with these two ideas, Fatty proved what is called the Fatty's-Wickham theory, that actually there exists a function u which is subsolution such that when we apply the semigroup to u, what we see is a translation of u minus c times the Mañé constant times t. And we will call this function the Wickham solution of our equation. Okay, I said before that we had to make a decision if we want curve that comes to negative values, or if we want curves that goes. These solutions are called the negative Wickham solutions, but for this talk, we will just call them Wickham solutions because we will not talk about the other ones. But somehow the theory comes in duality. Okay, so first, u is, when u is a Wickham solution, then TTU is just u translated, so u is a fixed point of the semigroup defined in the quotient of the continuous maps over the constant functions. It can be shown also that only for the constant c, there are Wickham solutions. And for this one, for this class, for the negative Wickham solution, that means that this is also an which we don't need to ask for.
So you froze after saying that only for the Mañé constant there are Wickham solutions.
Okay, what I say is that it turns that for this kind of Wickham solutions, that means for the ones built in this way with the curves that comes from negative time to 0, U is a Wickham solution if and only if U is a viscosity solution. So it provides an alternative theory to find viscosity solutions for this equation, for sure. And also, if we take any subsolution, it can be shown that when we apply our Laxo-Legnik semigroup to U and we sum up this constant, but otherwise the function goes to, well, plus infinity or minus infinity, depending on the value of CH, it converges to a Wickham
So we're having some technical difficulties. We're reaching out to Sebastián to see when he can come back. ¿Es algo?
Sorry for that. Sorry for that. Let's see if now we have better internet. And we were somehow here. Or no, here. Yes. So I think so.
Seeing the correct slide.
Yeah, we're
Huh?
We're in the title.
We're in the title?
Yeah. We're not seeing what you are seeing, it seems.
Okay.
No, okay. ¿Ya se ve? ¿Sí? Ahora le voy a poner full screen. A ver si se sigue viendo. ¿Se sigue viendo?
Yeah,
Perdón.
No,
No vemos el
no vemos el full screen. Ese es el problema.
Yeah, okay. Now can you see it?
No, we see just the bar,
The toolbar.
The toolbar.
Really? Okay, yeah, I can
Yeah,
see
yeah,
it.
it's super weird.
Ay.
Comparte toda la pantalla.
Comparte la pantalla.
Ahí se ve, ¿no?
No, pero no solo eso.
Ahora
Eso.
vemos el navegador.
Put everything. Vale. Now?
Ujú. Sí.
Okay, good.
Ponlo-
I will go there.
Okay.
I will keep it there.
Yeah, thank you.
Again, sorry once again for the inconvenience. Okay, so another way to define weak KAM solutions is only by curves. So we say that U is a subsolution, and therefore we have the inequality written in red, but with an inequality for every curve that connects gamma B and gamma A. And for every x, there is one curve such that we have equality. So actually we can understood this gamma as a sort of gradient flow for you, or as a Lagrangian gradient flow that matches the cost of moving through the space using the Lagrangian. And yeah, and so for that, we may think that when we goes to minus infinity, as in the case of complex functions or C1 functions, we could be going towards critical points. And we will state this properly. Okay, so we have here that curves characterize weak KAM solutions. So now let's try to build a weak KAM solution only using curves. This is the next goal. So we recall that we define ht as the minimal action in time t to reach y from x. And we define the Paris barrier function as this length. So we take the curve that takes, like the domain of the curve goes to infinity, and we have to get rid of this constant, or the Riemann constant times t. So the first question, is this h well defined? This is somehow the only proof that we will do together, because it's an important part of the theory and it reveals more details, more stuff. So first, we know that there exists a weak KAM solution and we will use it. So we know that U is a subsolution. Therefore, we have this inequality. This inequality is just being a subsolution for all t. We take t to infinity, or as a limit, and we realize that h of yx is greater than minus infinity. Okay, so now we need to show that this limit is not plus infinity. For that, we first show that there exists a point that hzz is equal to 0. Okay, so, and if we realize, if we put hzz, we have that this is greater than 0. So we need to show that it's lower than 0. So fix x in M any point, and let me gamma be the curve such that witnesses that U is a solution in the weak KAM sense for x. So we have that U gamma B minus U gamma A is equal to this integral. Okay, now take Z any alpha limit of the curve, because the curve is defined till minus infinity. So, and since the space is compact, we have one accumulation point. And we claim that for this accumulation point, or any accumulation point of the curve towards time minus infinity, we have that hzz is equal to 0. Indeed, take Tn a sequence of times that goes to minus infinity such that z is equal to gamma Tn, and such that the span of the time goes larger and larger, because we want curves that are defined in larger times, Now we define the curve eta n, nu n, sorry, such that it starts in z, then it goes with a geodesic to gamma Tn plus 1, so you can imagine the red curve. We move through gamma till the next time, or the previous time, gamma Tn, and then we come back with a geodesic from gamma Tn to z. This is a curve that the time that it takes is at least Tn minus Tn plus 1. So the length of the time in which the curve Vn is defined goes to infinity as n goes to infinity. And we can estimate hzz, which is the liminf of ht of zz, as the limit by using the times, or the liminf, by using the times given by the length of this curve eta n, nu n. So, and actually this quantity, it can be estimated by the curves that we just built, and this show that is equal to 0. So now we just have to do the computation, but it's the way to prove it. Okay, so we have proved that hzz is 0. Now we need to prove that for any xy, hxy is smaller than infinity. For this, we realize that using dynamical principle, the action or the cost for moving from x to y in 2 plus t seconds is actually lower than moving first to z, staying at z for t time, and then moving back to y. We plus, okay, I don't know if you see that. Can you see it or? Okay, good. We plug the 2 plus t times the constant, the Magne constant. We take the liminf. We know that for zz it goes to 0, and we get that is lower than plus infinity. So this function is well defined. The proposition. Okay, we build it, but we will not make the details. Hx dot is a weak KAM solution for any x in M. Actually, by definition, it can be easily proven that it's a subsolution because of the dynamical programming that we use also in this step, in this third step of this slice. But also by using Arcellas-Colli theorem, we can show that there exists this limiting curve that is defined from minus infinity to 0, such that the above expression actually is an equality for any y equals to gamma 0. Which time is it? 33. Good. Okay. So this function, which is called the Perez barrier function, provides a clear way of how to build weak KAM solutions only using curves. Now here we don't use, however, we have proven that it's well defined by the existence of a weak KAM solution. But if we were able to get this in advance, it's already a weak KAM solution only defined by using curves. Okay, now let's move toward the fact that actually the equation has a boundary. So the projected overset is defined at those points in M such that hxx is equal to 0. Okay, we have seen this before. Actually, when we took a solution, a weak KAM solution, we took one of the curves that have the quality in the definition of weak KAM solution, all the alpha limits satisfies this. So we have already proved that the overset is non-empty. Moreover, if we want to see the example for the classical or the mechanical Hamiltonian, the overset coincides with the argmax of the potential energy. Okay. And as I said before, AH, the projected overset, can be seen as an intrinsic boundary of the equation, the Hamilton-Jacobi equation. Why? That's the important part, say. Because if we take U as solution, we take any x in the manifold, we take any curve gamma, a Lipschitz curve such that we have the equality for all s, we know that this curve somehow lands at minus infinity to the overset. So this says if we know the values in the overset, we can actually integrate backwards or forward because we're starting from minus infinity from the overset towards x to get the value of x. And actually, this holds like that. If U and B are two weak KAM solutions and we have a dominance in the overset, then we also have the dominance in the full manifold. Okay, so this is a maximum principle. So, and the maximum principle is stated in the overset. Well, it can be done in a smaller set, but this will be a bit more complicated to define it in this talk. Okay, and the whole time I have called the projected overset. So it should exist the overset itself. And it does. So there is a surprising property of the overset, which is the following. For every point that belongs to the overset, there exists one covector or a vector in the cotangent bundle such that the derivative or the differential of u at x is always p of x, and we have the equality for the Hamiltonian for every subsolution. In particular, for every solution. Okay? So the overset is just the set in the cotangent bundle that contains the information on the manifold and also of the cotangent vector. And actually, with our hypothesis, like everything is C2 Tonelli, it can be shown also that the overset is a Lipschitz graph. So this, as a function, is Lipschitz. Okay. Let's keep moving forward, because now the goal will be to see what happened in the unbounded case or the non-compact case. But for that, we have to go now to the work of Contreras. Before was mainly stuff done by phi t, I think. Okay, so there is something called the Magne potential, which is defined as follows: is for xy is the infimum of htxy plus tch for t greater than 0. Okay, here I would like to recall that our Lagrangians are superlinear. Therefore, if t is really small, htxy is very, very large because moving fast is expensive. So this infimum is not clear where you find it somehow, or at infinity or not. Actually, it can be shown that it's not at infinity, but it will not be at 0, that's for sure. Its phi is a symmetric and satisfies triangular inequality. And there is first theorem by Contreras, which actually says that phi, h, the Paris barrier function, which is defined as the lim-inf of the expression above, actually is written as the infimum of this sum, in which what it says, for computing the Paris barrier, which is the lim-inf of the expression above, what the curve does is goes as fast as possible to the Aubry set. It remains there for a long time because remaining there costs 0. This is the definition of the Aubry set. And then goes back to the right point y. So actually, this is the intuition of that every curve that witnesses to be a weak solution goes to the Aubry set. And moreover, we can recover all weak KAM solutions by this formula, this representation formula. That all the information that we need is on the Aubry set, and what is outside, we get it from the Magne potential. Okay, but Contreras had in mind to do this theory not in compact sets. So, which are the problems in the non-compact case? Well, too many. First, the curves that witnesses to be a weak KAM solution may have not accumulation points because it may goes to infinity. If this happens, then maybe the Aubry set as we define it is empty because we will not have accumulation points. It was the way that we prove it. And so Magne, the very first definition of the Magne constant was actually the following. Define the Magne potential in blue, but with an arbitrary constant, C. And consider CH as the one that makes phi to take non-minus infinity values. For this, for sure, we need some properties on the Lagrangian. Like not for any Lagrangian we will have this property. But if it is C2 uniformly convex and uniformly coercive or uniformly superlinear, we will have it. But in any case, even with this, the Aubry set can be empty. So the result of Contreras says we can develop the theory using the Magne potential instead of the Aubry set. So if we are non-compact, we define what we call static curves, which actually are the curves that we use to witness weak KAM solutions, but using now the nomenclature of the Magne potential. And what we can show is that the U gamma defined as this limit actually is a weak KAM solution. And here, okay, if there is Aubry set, and if this curve at minus infinity goes to a point in the Aubry set, okay, we will have that this is phi of zx minus a constant, which is, okay, it's a weak KAM solution in the way that we have defined it before. However, if the curves goes to infinity, this is something new. And it's called Bussmann-Wickham solution because it's related with what we call the metric compactification built by Gromov, and in particular to the Bussmann functions defined in the ORO boundary. So this is, from that place it comes the word Bussmann. And if this happens, it can happen for every curve, and so the offset can be found at infinity as this ORO boundary built by Gromov. In this sense, more or less. Okay, let's summarize a bit. We have built the Laxo-Legnic semigroup with which we prove the existence of our weak KAM solutions. Actually, we defined it first by using the Laxo-Legnic semigroup. Then we got the Aubry set, which is an intrinsic set for the equation that acts as a boundary for the Hamilton-Jacobi equation. Moreover, we found that in the compact case, there are predetermined differentials for the solution, subsolutions. We got the Magne potential that allows to recover weak KAM solutions, and also it can be used in the non-compact setting. And okay, we mentioned a bit the Bussmann-weak KAM solution, and that they relate to some compactifications of non-compact spaces. So a bit of some words about what we can find nowadays, and it's how to do this theory, but in the metric case, inspired because applications in networks or, I don't know, Basel spaces, whatsoever. So first, we can think on defining a Laxo-Legnic semigroup and try to study the solutions as we defined at the first slides, the weak KAM solutions. And this has been done by Savidovic, and he published now this year a book on discrete and continuous weak KAM theory. Or also we can take the semimetric phi and consider it as a Magne potential and try to build everything, because we know that we can recover weak KAM solutions using the Magne potential. This line can be found in the lectures at the Universidad degli Studi di Roma, and it was done by Albert Fati. Okay, so if time allows, I think we have time for one. This was more or less the introduction to weak KAM theory and trying to explain important concepts of the theory. For sure, there are more involved, but this could be seen as an introduction. And now let's talk about convex functions. So let's fix H Hilbert space, Fg continuous convex functions, and we define the slope or the local slope of F as the lim sup of this value when y goes to x, and we only take the positive part. That means if this value is negative, we don't consider it. It is known that this actually coincides with the minimal norm of the subgradients at x. So one question will be, does the equality of slopes implies that f is equal to g plus constant? I know that it's very well studied. Your team by David, Emilio, Pedro, Aris here, and many others. And restricted to the C1 case, actually this is exactly the same as saying whether the aconal equation, if it has two different C1 convex solutions, do they coincide up to a constant or not? Okay, so we know the answer. The answer is if they are bounded from below, then yes. And this in the Hilbert setting was done by Pedro, David, and Emilio. And moreover, we have a representation formula, which is the infimum over following curves. And this infimum actually is a minimum. And the minimum is just the argmin of the arc length parametrization. Yeah. And actually, along this argmin, we have the equality f gamma a minus f gamma b equals to the integral. So the analogy with weak-KAM theory, f could be interpreted f as a weak-KAM solution. If f has critical points, then the Aubry set will be the points in which the derivative is zero or the slope is zero. In this case, the associated derivative for x in the Aubry set is zero. And if f has no critical points, then the Aubry set is at infinity because the gradient flow escaped to infinity. So somehow it's a clear analogy. There is another somehow point of view of the same result. The unbounded case. Clearly, if the following equation has two convex functions, two convex solutions, which are not equal up to a constant. Take any two linear maps of norm 1 which are not the same. Okay, but we found the following result together with David and Aris, that if f is a lower semi-continuous convex function, then for any subgradient curve, we have that pf, well, we have that the limit of the minimal gradient at the subdifferential, minimal subgradient norm at the subdifferential at gamma t converges to a given vector. And this vector is independent on the gradient flow, or where it starts the gradient flow. So somehow we could say that the derivative of the gradient flow goes to minus pf because we have the minus in the differential inclusion. And actually this is right because for subgradient flows, we have that the right derivative of gamma dot is equal to minus the subdifferential of minimal norm. Okay, and we can prove the result for C11 convex functions. So if they have equal slope and they have equal Patsy-Grandal directions, then they are equal up to a constant. Here, the Aubry set lies at infinity. And in this convex setting, we can prescribe a derivative at this infinity, which is the Grandal-Patsy direction, that allows us to determine the convex functions. So again, we recover the analogy with weak-KAM theory. And yeah, I think that due to the technical issues, I will skip the second related topic. Sorry for the technical issues once again. But the references, maybe it's the most important part. For the weak-KAM theory, I took three main references. First, I will say that the book of Fatih is very well detailed and is a preprint from the 2008, but is free in internet. Also, I followed the notes of Rifford, Ludovic, on regularity of weak-KAM solutions. It was a seminar that he gave in École Polytechnique on the year 2011-2012. And for the unbounded case, I took the paper of Gonzalo Contreras. Okay, for the metric weak-KAM theory, there are these two main sources by bibliographies. The first is the one of Fatih, the lecture notes given at the University of Rome, and the book of Savidovic on discrete and weak-KAM theory. And just to finish, because why not, a bit of self-publicity. Related topics that of my own that relates weak-KAM theory. The first that we talk about is determination of unbounded convex functions via Grandal-Patsy directions. Also that sadly, we don't have time. The work with Min Le, which is a co-author, and here also from Vienna, and myself on discounted global eikonal equations, and that this relate the metric Wickham theory. And the last one is a topological study of what we call the Gromov compactification that relates with the Bussmann solutions found by Contreras. Okay. I come back here and thank you very much.
Thank you, Sebastian, for this very nice talk on this very deep subject. So we have time for a few questions. So if anyone in the audience has questions, now's the time. Director.
So, thank you, Sebastián, for this quick introduction. It's a lot of to digest, but if someone would like to get into this subject, try to work on it, what should be the, I don't know, one or two problems to explore? Something that is something to do, or some interesting questions to explore.
Somehow it depends on the flavor of things that you like to do. Because it's a theory that comes from 2000 or the late 90s, right? And we got into this theory mainly with my co-author here in Vienna, because we bump into the global slope, which it turns out to be related with a Lax-Oleinik semigroup defined on metric spaces. Somehow the theory in general metric spaces like non-compact or non-locally compact is, I don't know, it's completely open of what to do. Now, if you like to do regularity stuff, yeah, there is also a bunch of questions on regularity, or to study some, I don't know, yeah, somehow it touches different sides, because the presentation that I gave today was more from the sort of analytic point of view of the Aubry set, but there is also the dynamic point of view using matter ideas, and that relates more with the invariance of sets for the Euler-Lagrange flow. And if you are in this line, also you can go. Sorry, and this. Okay. So yeah, on my side, what I can say is that I'm more related with the metric side of the theory, and so I can imagine more questions in this side. But if your flavor is to do more in something more related to PDEs or more related to dynamics itself or invariance theory, yeah, there are also things to do. Okay. Yeah. Yeah, but also, sorry, the last thing is that what I like this theory is because it allows me at least to see the same problems that I have working before with a different point of view. That somehow that equations contains intrinsic information that can be called the critical set or can be called like the right curves to flow with.
So do we have any other question? So I have another question, a much superficial one. Where does the name come from? Like KAM? Sounds like an acronym, but
that's a good question. Because I didn't explain it. KAM theory is Kolmogorov-Arnaud-Morse theory, and it studies the invariance of tori in Hamiltonian dynamics or Lagrangian dynamics. Somehow with KAM theory, and in KAM theory, everything is smooth in some sense, because we have some tories in our cotangent bundle or tangent bundle that are invariant for the Euler-Lagrange flow or the Hamiltonian flow. Somehow the weak KAM theory comes into play for asking the minimal level of energy in which we can still have some invariance. And the minimal energy, level of energy, is actually the Magne constant. This is the first thing that we did, to put all these smooth solutions or smooth function and put it down. So weak KAM solution could be, because it's a theory on invariance, but for in the non-smooth case, because we are in the critical case.
Nice. Thank you very much. So if there are not any other questions, then let us thank Sebastián again for this very nice talk. And so I'm not sure when the next talk of the seminar is. You can check on our website, and of course, we will send an email with the invitation and the link to the next session. So thank you all for coming, and thanks again, Sebastián.
Gracias, Sebastián.
Thanks to you for inviting.
Bye bye.